okay, I already had the lemma 0, which basically was kind of a tautology, but it was important to notice this tautology because it was because of the regularity. Here we really use the regularity in an essential way. Now I want to say the following, that I want to define another graph. Okay, so that we will do the following. I want to say that the, okay, let's call it lemma 1. The discrepancy of x tau of sets A0, A1 up to AD. Eventually, that's what we want to. This is really what we want to bound. Is at most the discrepancy of the following graph. Let's look at the graph that we called before BI. So remember what is BI? Was the graph such that on one side of it we have VI, on the other side of it we have the walls of all the walls of type without I, and some edges between them according to the definition. You know, if together they create, they form a chamber. So I take this discrepancy of BI of the set. So I take here 0. Now A0 is a subset of BI, so that's fine. Now I have to put on the other side, now I'm talking about discrepancy in a bipartite graph. In a bipartite graph, I have only two sets that should be put. On one side, I have to put a set in VI. In the other side, I have to put a subset of this. The subset of this will be all the walls of A1 up to AD. So I take the walls of type A1 up to AD, namely all the walls without 0, but such that the vertices inside them are in A1 up to AD. And I ask what the discrepancy in the bipartite graph, but this is not the end, plus AI1 divided by A0 divided by V1 by V0 times the discrepancy in X of the set A1 up to AD. Now, I wrote the lemma in this way with the 0 because I didn't want to make too many notations, but we are going to use it also with different indexes, and you will understand that this is exactly the same thing. Okay, we'll come to it.
Should BI be 0?
What?
Should BI be 0 or?
Where is VI?
Discrepancy.
Hey, you are right. VI is oh, yeah, right. So this is B0. Yeah, that's exactly. Yeah, I said that I'm doing it for 0, but I will use it also for the others. But let's put it just for the zeros. So I really should write B0. Okay. So I can bound the full discrepancy. It's kind of an inductive process. I can bound the full discrepancy by a discrepancy of this bipartite graph plus something which is less than 1. Okay, and you'll see that if somebody wants to be very, very precise, I'm really giving up on information here. If it's really small set, it's much less than 1. Times the discrepancy of that set. Okay? And then we'll continue this by induction after that. But let's prove first this lemma. And the proof is just a computation, but let's be careful. So what is this? By definition, this is the size of E A0, A1 up to AD divided by the full, by E of V0, V1 up to VD, right? The total number of edges, maximum faces, minus the product of J goes, or I goes, from 0 up to D of AI divided by VI. And this can be written as E of A0 against E of A1 up to AD. Now this is edges in B0. You see, the number of chambers, A0, A1 up to AD, is the same as the number of edges between A0 to walls. This is the set of walls of type A1 up to AD, right? In the bipartite graph B0. Do you see that this is the same number? Divided by this number. So we just call it maybe E of X. This is just E of X, like the total number of edges of X. When I say edges, I mean maximal edges, right? Like maximal chambers. Okay? E of X. Minus AI0 divided by VI0 times, let's give this a name. I will call this E prime minus E prime divided by E of D minus 0. Now, you don't even have to understand what I write it, because I will do this minus plus exactly the same thing. So I'm certainly allowed to do it. Even if I sometimes don't put the E of D minus 0. Minus, so I we'll come back to that in a second, but I subtract something and I add something. Minus, no, I'm sorry. Yeah, I do this like that. Plus this, in brackets here, minus the product I goes from 1 up to D of AI divided by VI.
Here you wrote AI0.
Maybe I'll bring a color to see that there is some brackets here which goes on this. So this is minus plus, I just added something. And this is minus what I had before.
You wrote there AI0, but I think you
It should be A0, so not A0, it's A0. I mean, in my notebook I wrote it with general notation AI, it doesn't matter, but I decided, you are intelligent enough to do it for 0, you understand that it works for everyone. Okay, so this is the same thing. And let's just to understand what we put here. We put here E prime. E prime is the number of walls lying on the set A1 up to AD. On the sets A1 up to AD. These are the codimension 1 faces whose vertices are on this. Okay, so now you can see that this is at most. This is at most. And now I can like triangle inequality. I can write this minus this. But now let's think. What I'm claiming that what is written here is exactly the discrepancy in the graph B0, such that on one side I have EA0 and on the other side I have something. Okay? Because what should I do? Because this is exactly what is written here. What is written here is written, think about this term and this term only. Right? Then on one side you have a 0, on the other side you have all the walls, the set of all the walls, which lying on the sets A1 up to AD. This is a set of vertices in the bipartite graph, B0 on the right hand side. And I have to divide it by the total number of edges. The total number of edges in B0 is exactly as the total number of chambers in the complex, because every chamber uniquely associated with an edge in this bipartite graph, such that on one side you have the vertex of color 0, and on the other side you have a wall without 0. Right? All chambers are like that. And every chamber is expressed like that in a unique way, as a one vertex of color 0 and one wall without a 0, which are connected between them. So this is exactly the discrepancy here. And now, plus A0 over V0 times what? Now we have to understand. So this is exactly what I promised you here. Plus A0. Now I claim that what is written here inside the brackets is exactly the definition of the discrepancy, that's clear, of A1 up to AD. Without A0, right? We define discrepancy of, I take a subset of types, right? And in each one of them, this time the subset is only the colors between 1 to D, without a 0 color. And we have E prime is exactly the faces with colors 1 up to D, such that the points are in A1 up to AD. Right? Divided by the total number of this type, the total number of these types of vertices of faces is this one, minus the expected value of them, which is exactly this one. So this is exactly the discrepancy in X of A1 up to AD without A0. Okay? There. And now let's prove the result. And now I have to bound oh no, I shouldn't. I made a mistake. There's something between. Okay. So finally, now, so we finished. This was proved. This was a proof of lemma 1, and now we can prove the the proposition. So what we have to bound? We have to bound the discrepancy of A1, of A0 up to AD. For all subset A0 up to AD, this discrepancy of X star. Right? Okay, well, we start with the discrepancy with capital D of X star. This is equal to the maximum on things like that. On discrepancy of A0 up to AD. So we have to bound this kind of thing. Okay, so let's see by dilemma. This is at most the discrepancy of inside B0 of A0 against something. Against A1 up to AD plus A0 over V0, the discrepancy inside X of the sets A1 up to AD. Right? This is lemma 1. Now, this is at most the discrepancy of B0. But the discrepancy of B0 is at most this lambda normalized. So this is at most the lambda normalized of B0. Right? Now plus 1, the discrepancy of this. But I can do now exactly the same trick. It doesn't matter because you remember. Okay, I'll do it slowly. This is by lemma 1. Now I'm going to use lemma 0. Lemma 0 told me that this discrepancy is the same as the discrepancy of X of the full set V0 A1 up to AD. You remember? That's what we did before the break. The discrepancy of X1 up to XD is the discrepancy of B0 A1 up to AD. Okay, are you with me? Now, there was nothing special. There was nothing special here when I proved lemma 1. I prove it for V0, for the first, but there was nothing special about color 0. This is the same as in all the other colors, right? So this is the same, so this will be at most. Now I'm using lemma 1, but the essence of lemma 1, right? Not formally lemma 1, because I'm using it for A1. So this is the same. Now, first of all, lambda normalized of B0 plus, now the new thing will be lambda normalized of B1 plus A1 divided by B1, the discrepancy of V0 A2 up to AD. Okay? Because lemma 1 told me that the discrepancy of A0 up to A1 up to AD is at most the discrepancy in the bipartite graph of B0, but now I'm using it on the bipartite graph of B1, plus A1 over V1, the discrepancy if I eliminate the set A1. Right? Are you with me, right? So, okay, and this is at most lambda normalized B0 plus lambda normalized B1 plus, now this I can replace by 1, plus, right, this is 1, this is at most 1, and this discrepancy, I can do it by the same argument. It's the discrepancy of V0, V1, A2, up to AD. This is again using lemma 0. And now you can see the rest, right? Now, and now I will go, and now I will eliminate A2, etc., etc. And then it will be eventually the sum. I think, by the way, we don't need the last one, if I'm not mistaken. It's really even lambda normalized of BI, because I think if we go from 0 even up to D minus 1, what will be left eventually? It will be the discrepancy what it will be eventually. It will be the discrepancy of when I stay here with only 2, and then I eliminate this one. So this is exactly the number of this one against all the other. I don't know, I'm not sure. Maybe we don't. I don't care. I don't know, if you want to think about it, maybe we don't need the last one. We can choose who will be the last one. Maybe it says something that some of the last one, which means that if you have a good estimate somehow on D out of the D plus 1, maybe that's enough. I don't know. Anyway, this is at most D plus 1, the maximum of these lambda normalized of this BI and the propositions.
How do you get the,
Yeah, questions?
why is the discrepancy go away at the end?
Why what?
I mean, at the end of the discrepancy, V0, V1 to VD, is that obviously?
I can't hear you.
Why?
Follow the pattern, again, the discrepancy, V0 up to VD.
V0, A2, AD.
So after you do all these by induction, you get discrepancy V0 up to VD plus this side of the normalized, right?
Yeah, but you're right. I'm getting a bad, but the discrepancy of this is 0. You're right. You see, the discrepancy, you're right, I have to say that. The discrepancy eventually, you see, I'm getting the discrepancy of V0, V1, V2, up to VD. I'm filling all of them, right? But what is this? By definition, this is the number of edges between them divided by the total number of edges, which is exactly the same thing. It's 1 divided by 1, minus the product of VI divided by VI. So it's 1 minus 1 is equal to 0. Good. Should be said. Okay, now let me give you an exercise which I don't know to solve. But I believe, and I think it should be useful. I don't know if maybe I don't know. I don't want to start the subject now because this will be in this semester. We will mainly work with the simplicial complexes, and I'm kind of going into the next topic will be buildings and quotients of building, with the idea to show that if you take quotients of the Boatitz building associated with some p-adic groups, then you are getting simplicial complexes with very small discrepancy, namely they are very good expanders in this sense, or if you want, they have a very strong mixing lemma. And this mixing lemma will enable us to evaluate various combinatorial properties of them, like chromatic number, like independent set, and also the overlapping, the geometric overlapping that I told you about, if you still remember, in the first lecture. In fact, that will be maybe the most important application, that they satisfy this geometric overlapping property. And the way, and this will come up by using the results of Bach, which I don't think I mentioned. I could stop here and explain why this is important, but I prefer maybe not to do it because I decided, you know, this is a joint course with Gil Kalai, and he will teach the second semester, and he will take more, he will teach this Bach theorem, etc. And then we will come to use the application. So meanwhile, you should take my word, and I think you get a feeling that these kind of mixing properties are strong properties. But still, I want to relate it somehow to the spherical complexes. And the exercise I want to give you is a challenge, because I don't know. You know, I showed you how to compute various bipartite graph associated with the spherical complex. Remember, we took dimension 1 against dimension 2, 2 against 3, etc. We didn't even do this in a very general, but the right one, which we really need, exercise, challenging exercise. And maybe it's not known, I mean, I don't know, but I think there are tools to do it. Maybe nobody was interested in doing this before. But I think it will have some application is take X to be S, this spherical building S, D, Q. I don't know, S and Q, dimension M, Q. You can talk about the general case, but if you want, why don't we can start with the small numbers. I think it's starting to be interesting, maybe with n equal 4, 5, something like that. And then evaluate this lambda of BI, or if you want the lambda normalized. The lambda normalized is not, I mean, the lambda normalized is really the second largest eigenvalue of BI divided by the first eigenvalue. The first eigenvalue is not that difficult to compute. It needs some work, but it's not difficult because let's see what I mean by that. So what it will be really BI? BI, it will be spaces. So on one side, so the BI will be bipartite graph. This is a bipartite, biregular graph, as we talked today. On one side, you remember we have the spaces of dimension I, but on the other side, we are going to have walls without I. All the walls without I, which mean flags, which is really flags without dimension I subspaces. So on one side we'll have, I don't know, some W's of dimension I. On the other side we are going to have something which will be a U1 inside U2, inside UI minus 1, inside UI plus 1, etc. up to inside UN minus 1. Right? These are the flags without anything of dimension I. So it's not difficult to see what are the degrees, at least from one side. The degree from this side is clearly Q plus 1. Because if I have a flag like that, which is almost complete except of dimension I, but UI minus 1 and UI plus 1 are already fixed. So the number of ways to complete it inside here is exactly q plus 1. So the degree on this side is going to be q plus 1. The number of walls can be computed. I mean, it's an exercise. You know, it's the number of subspaces of dimension 1, and then the number of subspaces of dimension 2 containing it, and then up to here is no problem. Yeah, like this is a standard exercise that we understand. Now we have to jump in this quotient. We have to jump and go to count the number of I look at the quotient, which is of dimension n minus I minus 1, and I compute the number of subspaces of dimension 2 instead of 1, so I jump over there, and from there on I continue as before. So we can evaluate. This is going to be a very long number, a very large number, and here we are going to have a relatively small number, the number of all, well, not so small, by the way. If I is in the middle, like if I is more or less n over 2, then that's a fairly large number. So I'm getting here a bipartite graph, and then if I know, and then I can compute also the degree from here, either directly, just thinking about it. If you fix W of dimension I, how many flags you have which start below it and go up to W, and then start after W and go up to the very end. Well, that's not. I mean, all this is a simple linear algebra that I'm sure you can fix. What is less clear to me is how to evaluate the eigenvalues here, because the usual trick that I showed you in those cases when I computed, then we took the adjacency operator of this bipartite graph and we took the square of it. And some of the square of it is associated always to path of length 2. And it was, in all the cases where I computed, it was possible to pass from a space from one space to another in a path of length 2. If you remember the J, the matrix J appeared. It was A square equal to the something, the identity, plus J minus something with some constant. And this was the trick. Now, it's not true in general. If I take a subspace of dimension 5, I take two subspaces of dimension 5, then I cannot find a wall connecting one of them. Right? They're not in two steps. They can have, somehow there might be a larger distance. And I'm not sure really how to do it. I mean, it's probably possible, maybe it's known. I'm sure it's somehow in the literature. I don't know if it's elementary or needs some representation theory, but I think it will be useful to know, because if we will have good bounds, I will be happy for a bound which will tell that for a fixed n, and q going to infinity, to show that this lambda normalized of bi for all of them, or on the maximum of them, is going to 0. I'm sure it's true, but I don't know to prove it. And I think a result like that will have various combinatorial applications. So let me encourage you to take the challenge. Okay. Next time, buildings. We'll go to the building of a periodic. Now, how many of you knows what are periodic numbers? Or let's ask, who doesn't know what are periodic numbers? Okay, so maybe a little quick review, but do me a favor and take a look in the book. Or even go to the internet, write periodic numbers, and read the one page on the basic definition somewhere that you will feel comfortable, because you will need it. we will work over the so-called local field. Local field, basically, there are two basic examples. It's either the periodic number, the so-called QP, or FQ. You take a finite field, and you take the Laurent power series over the finite field with, so these are all the Laurent power series, formal power series over FQ with things like that, sigma AI, e to the I star in some m up to infinity, with m any integer, can be also negative. And this is a field, you can multiply them, etc. These are the two types of local field that we will work with, so you should be kind of comfortable with working with what are periodic integers, etc.